This video is about sigma notation used in summing series. So sigma here is capital sigma, it's a Greek S, S for sum, sum is adding, so that's what sigma notation does. It's a way of saying that we're adding up some terms, and the way it works is like this. So I've got the sum, so that's this symbol here means that I'm going to be doing some adding, and I've got some definition of a sequence, like an nth term definition here. So this one is just n squared plus 3. So that's again a sequence. So if it was xn equals n squared plus 3, then we'd have x1 is 1 squared plus 3, so that's 4. x2 is 2 squared plus 3, so that's 7. I would have x3 is 3 squared plus 3, which is 12. x4 is 4 squared plus 3 is 17, etc. So what this notation says is start with n equals 1. So this one, the one we put at the bottom here, is the start, and this is where we end. Now you don't actually necessarily write n equals at the top, but it does mean for the same value, for the same letter as at the bottom. So it's going from n equals 1 to n equals 5. Add up the terms of this sequence. Okay, so I've written most of them down here. When I put 1 into this, I get 4. When I put 2 into this, I get 7, so it's 2 squared plus 3. When I put 3 in, I get 12. When I put 4 in, I get 17. And then finally, the fifth term of the sequence here is 5 squared plus 3, that's 28. So this notation just means add together all of those values, starting at 1, ending at 5, the value of n squared plus 3. So that's 11, 23, 40, 68. So this evaluates just to a number, 68. Here's another one. No reason it has to be n in the sum. Here I'm going from p equals 7 to 9 of 3p plus 4. Now, usually this will mean this is all in brackets, so I'm taking 3p plus 4 and taking it for the values of 7, 8 and 9. So I'm starting at 7, so the first one is 3 times 7 plus 4, and I also add on 3 times 8 plus 4, and I also add on 3 times 9 plus 4, so this is 25 plus 29 plus 33. It's actually just the 3 successive terms in this arithmetic progression. So let me just write that a bit more neatly so it's not so confusing. So I just need to add those 3 terms together, so I've got 77. And this, letter P is what we call a dummy variable. It's like a placeholder. So P itself doesn't appear in the final answer. This doesn't depend on P. So I could replace P with A, and as long as I change this to A as well, it means exactly the same thing. It'd still be 77, because that's just a placeholder. It's saying whatever is sitting wherever A is, or P is, or whatever I want to put in there, I replace it with 7, and then replace it with 8, then replace it with 9, and then I add those things up. So you could use any symbol you like here. We could have a smiley face or something, sum of smiley face between 7 and 9. That just means replace that symbol with 7, then with 8, and then with 9. Now, here's another one. I want to do 5 times the sum from k equals 4 to 6 of k plus 5. Now, you've got to be a bit careful with this series notation, because it's slightly unclear when you write it like this whether I mean I'm adding up k plus 5 between 4 and 6, or whether I'm just adding up k and then adding 5. So let's just see what the difference would be here. So this means do 5 times this whole sum. So it'll be 5 times this sum. So when I put k equals 4 in, I get 4 plus 5, that's 9. K equals 5 gives 10, and k equals 6 gives 11. So that would be 5 times 20, which is 5 times 30, which is 150. Whereas if I'd said 5 times the sum from k equals 4 to 6 of k, and I'd sort of meant it like that, and then adding 5, I'd be doing 5 times just 4 plus 5 plus 6, and then adding on 5 afterwards, so the sum here would evaluate to 15, and so I just have 5 times 15 and then add on 5, so that would give me 80. So sometimes these things aren't written down very clearly. I think if this had been written just sum of k plus 5, I'd probably have assumed it meant the top one here. But you know, as always, we've got to try and be as careful as we can with our notation so we don't avoid ambiguity. So we do avoid ambiguity. This one might be a little bit confusing. I've got the sum from t equals 1 to 4 of a times t. Now, just got to be careful here. It's t in the sum here, so I'm going to replace t with 1, then with 2, then with 3, then with 4. So when I replace t with 1, I get a times 1, that's a. Then when I replace t with 2, I get 2a. T with 3, I get 3a. And t with 4, I get 4a. So this is 6a, this is 10a in total. So don't be confused if there are other letters around. We just treat them as if they're there, and it's just the t that we're going to replace. No reason we couldn't have negative numbers in the sum here. Then you sum from minus 3 to 5 of x squared. That would be minus 3 squared plus minus 2 squared plus minus 1 squared plus 0 squared plus 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And if you add all this together, you get 69. And here's one that people sometimes find confusing. If we have the sum from p equals 4 to 8 of 3, what does that mean? Well, this doesn't have any p in it. So if you think about what happens here, when I replace, you know, p with 4 here, well, there's nothing to replace. So I just get 3. When I replace p with 5, well, there's nothing to replace. So I get another 3. When I replace p with 6, I get another 3. When I replace p with 7, I just get 3. When I replace p with 8, I get 3. It's a constant sequence 3, so this one just evaluates to 15. Think about it in terms of the sequence. What I'm saying here, you know, if this was the sequence, you know, xp is always 3. You know, this sequence just goes 3, 3, 3, 3, 3, 3, 3, etc. And I'm saying just add up the 4th up to the 8th terms of this sequence. So 1, 2, 3, here's the 4th, 5th, 6th, 7th, 8th, here are those terms. I'm just going to add up 3 plus 3 plus 3 plus 3 plus 3. Anyway, so there we go, that's how sequence notation works. The sigma notation, we just substitute whatever value we've got if it appears in the sequence, and add them all together. So sigma for summation is adding together terms of a sequence.